When pressurized air is rapidly depressurized, like when a can of soda or bottle of beer is opened, or like the air coming from an air cannon after it is fired, the air will appear misty. What thermodynamic process best models this situation, and what is the mist comprised of? And in case you're not sure what I mean by the air cannon, sometimes it's sporting events or like in big amphitheaters, they'll have these like air powered guns that shoot like a t-shirt into the crowd, and then you'll see this big cloud of mist coming from it. So that's the kind of thing I'm trying to describe there. And what all of these have in common is we're talking about gas that is mostly air. One could argue whether it's maybe a little bit different than air in the case of the soda can or the bottle, that is rapidly expanding out into its environment. In the case of the air cannon, it's rapidly expanding and maybe pushing, it's either pushing a t-shirt, or sometimes they call them a spud can because maybe it's pushing some potato or something out through the barrel. If we look at the four identified thermodynamic processes, I don't think isochoric makes sense because that's constant volume and the gas is definitely expanding. Isobaric likewise does not make sense because the problem literally says pressurized air that is rapidly depressurized, so clearly pressure is not constant. Isothermal might sound like a good candidate, not knowing anything else about this situation, but I'm going to have trouble, I think, explaining that mist based on isothermal. So what about adiabatic? What would things look like if I modeled this as an adiabatic process? So for an adiabatic process, heat is equal to 0. So that would mean that the change in thermal energy is equal to the negative of work done. Now, particularly in the air cannon example, we're talking about a lot of work done by the air as it expands through a barrel and pushes a shirt and or potato out of the cannon. And where does, if it's adiabatic, like where does that energy that goes into that work really come from? It's not coming from like a burner or something like that. It's not coming from, because it's an air cannon, it's not like it's not a gun, so there's no like gunpowder or some other chemical source of energy there. I don't think the assumption of adiabatic would really work for those. So where that work really comes from is a drastic reduction in the thermal energy of the gas that I'm calling air most of the time. But again, maybe in a can of soda or in the bottle, there might be a little more CO2 in there, I suppose, than normal air would have. But either way, that gas is losing a lot of thermal energy, which means its temperature goes down. And it turns out that's the thing that's going to let me explain what that mist is comprised of. Because when temperature goes down, we know that when temperature goes down, water would condense into liquid water. But what if the temperature went so low that it's below the freezing point? Then that mist, instead of being liquid water, would actually be like little tiny ice crystals that condense in that super cooled air. And it turns out that actually is the correct explanation. So let's go and check the answer. It says adiabatic process and ice crystals. A way that of thinking about it that makes adiabatic process make sense as a correct answer is that these processes that are described here happen very, very quickly. And it turns out that if something happens very quickly, there isn't really much time for heating to happen. So that lends itself to why the adiabatic process is a good model for this type of situation.